This video describes the first part of Chapter 2, discussing position and displacement and how we represent motion. We'll go through definitions of position, displacement, and distance, and then applications of each of those things with a few short problems. This picture on the right we'll come back to as an example of position and displacement. The idea that we're looking at here is a branch of physics called kinematics, and it deals with describing motion, and in fact giving a quantitative, meaning a numeric representation of motion. So we think about this as going from reality, which is motion, to model, which is kinematics. This kinematics then provides a mathematical description of the motion. However, it doesn't get into implications of motion, like cause and effect. So position is the first thing that we'll describe. Position tells you where an object is relative to an origin. In other words, you need a place from which you describe where an object is. You might say that Science Hall is 400 yards away from the lecture center. The lecture center then becomes the origin and Science Hall is the object. Or you might say you're standing at the back of the room. You're describing the back of the room relative to the front of the room. Position, because it has a sign, particularly when we're dealing in one dimension, is a vector. So it indicates either a positive direction from an origin or a negative direction from an origin. For example, if we want to find the position of an object at 2 meters, we say, aha, XA is the position of this object at plus 2 meters, and that little green arrow points to its location. So the plus 2 meters tells us where we are in the number line, and it's in the positive side. The position of an object at minus 3 meters would be there where the little blue arrow is. The arrows are just indicating the location. They aren't indicating a length. We do a lot of drawing pictures, and I will repeat this information a couple of times, many times in fact, throughout the semester. Every time we want to solve a problem, we make a visual representation of this problem. The little picture on the right is an example of that, where you see that visual representations are an integral part of understanding the physics in the problems and making models for them. And really, it is the most important technique you will learn. So here's an example of a picture, which is actually little snapshots. They're frames, and it's an example of how we can keep track of an object's position. So let's say we want to analyze the motion of an object. We need to know where it is at different instants. This means looking at its position at different moments, different instants. When the position doesn't change, the object is at rest. If you look at this set of frames on the right-hand side here, the frame number indicates an increment in time, and the little figure here is moving. So we see in frame 1, the little figure is right there. Frame 2, the figure is there, etc. It looks as though the figure is not moving, or moving in such a way that we can't determine it, from about this frame to this frame. And then here, we see a leg start to move again. So the figure must be moving again between these frames. So this is one way of describing the motion, and we can see here that when the position of this figure is not changing, the object's at rest. When the position does change, the object is moving. Now, we can turn that information into a graph, which we will focus on in this section and in class. This graph shows the position in the frame, which is being defined as the distance from the left edge, and the frame number. So from the first frame, the figure walks forward, the person walks forward, and then pauses in the center frames that we were discussing before, frames 8 through 12, and then walks backward in these frames. So here we've turned motion into a graph. If we calibrated it by distance and time, if we had that information in order to do that, we would then have what's called a position versus time graph. So this figure is the calibrated position versus time graph, where the vertical axis is position, referred to as x, and the horizontal axis is time, t. The origin is arbitrary, and we will determine that, we'll understand that with a few examples. So here's a different position versus time or graph, and in fact this is an earlier graph. This is distance versus frame number. How would we describe the position relative to the edge of the frame at frame 240? So we look here, we find frame number 240, and we locate where the graph is at this time. And if I made an estimate, I would take that line across to my vertical axis and find that somewhere between 27 and 28 millimeters from the edge of the frame. In the figure analyzing the person's motion, the origin was chosen to be the left edge of the frame. However, we don't have to choose the origin to be that location. Instead, we could move it around. We could say that the person's position in frame 1 is at the origin, and that the clock time also changes. And what you notice is that the shape of these dots didn't change. The relative positions of the data points did not change, no matter where we moved the axes. You could imagine just floating this graph, this particular plot around within the axes, and it wouldn't change the relative positions. Therefore, the origin doesn't actually matter when we care about relative positions. Displacement is something that describes the change in position from an initial position to a final position. In this figure, this is a large frame of what we were analyzing before. The arrow that points from the initial position to the final position is called the displacement. And this is a particular physical quantity. These arrows will be very helpful to you. Draw a picture and draw this arrow from the initial position to the final position. And what we will notice is that this arrow, this displacement, the length of the arrow, does not depend on the origin. I can have an initial position and a final position at these two locations, and the origin is not important. Let's test out a displacement here. So we have a different plot, and we'd like to find the displacement from frame 1 to frame 10. What this means is, what is the change in the position value? We find that by subtracting the initial position value from the final position value. So let's write it all out. The displacement is the final position value, which is 15 millimeters, minus the initial position value, which is 30 millimeters, and that's equal to minus 15 millimeters. So the displacement in this case is minus 15 millimeters. We see that this is negative, and a negative displacement means that the object was moving in the negative direction, or that at some point it was moving in the negative direction. Get back to that. So, in summary, the x component of an object's displacement is the change in its x-coordinate. We find it by subtracting the initial x-coordinate from the final x-coordinate, and this displacement is independent of the choice of origin. So the x component is measured along a specific x-axis, and it can be negative or positive. Now, distance is a different thing. Distance traveled is the distance covered by a moving object along the path of its motion. It's what you think of as distance, as how far you went. And it's different from the x component of displacement. One difference is that distance traveled is always positive. You can't go negative. You always have to go somewhere. Here's an example. If you were going from Science Hall, which on Google Maps, looks like my arrow moved, is actually not on Google Maps, but does exist. Yes, it's right there. And the distance from Science Hall that Google Maps determined to Main Street Bistro is 0.5 miles. These blue dots, the walking dots. The displacement would be this red arrow from the starting point to the final point. And we would guess that you had to walk a little further to follow roads and paths than you would if you could, say, as the crow flies, you know that expression, if you could simply go directly there. So we notice here that displacement looks like it's less than the distance. The distance is how far you actually walked, and the displacement is the difference between the final position and the initial position. Here's an example of position and reading these graphs. In this figure, the question is, how long did it take this object to get from x equals 2 meters to x equals 3 meters? So let's answer that question before answering the second question. At x equals 2 meters, it's at approximately 20 seconds. Let's say 20 seconds, right here. Now, as time goes, this position changes, and it looks as though at 30 seconds, the object is at 3 meters. Okay, so one answer is 20 seconds to 30 seconds, which is 10 seconds. It keeps going. It actually goes back to 2.25 meters, and then up again to 3 meters at 60 seconds. That means that another time it took from 2 meters to 3 meters is 20 seconds to 60 seconds, which is 40 seconds. So there are actually 2 correct answers to this question. This can happen. Imagine throwing a ball up in the air. It passes the height of your head a couple of times after it leaves your hand. We could also ask a displacement question about this figure. What's the displacement from t equals 10 seconds to t equals 90 seconds? The position is at 0 at 10 seconds, and is at 0 at 90 seconds, or let's say 92 seconds. And therefore the displacement is actually 0. Final minus initial position gives us 0. So in summary, the position tells you where an object is relative to an origin. The displacement is the x component of an object's displacement, which is the change in its x-coordinate. And the distance traveled is the distance covered by a moving object along the path of its motion. So continue on to review these sections in the book, sections 2.1 to 2.3, and practice worksheet problems and homework.